I'll not say very much, except that I've worked with STPA for a couple of years now. John has been helpful in learning me how to use it in practice, so I've got some practical experience. And I'm very happy for you to be here, John, and share some of your wisdom, which I think is very applicable. We're going to talk about safety-driven testing and self-driving cars and interesting stuff, but it applies to complex systems too, and a lot of other things in testing. But we can talk about that later. I think I'll just hand it over to you, John.
Perfect. Okay, thank you.
Oh yeah, one thing I mentioned is that everyone is free to ask questions in the chat and participate in the chat. I'll make notes, so I'll help and make sure that everyone gets their words and questions asked. So that's kind of my job here.
Perfect. Okay. We're going to do an interactive webinar. The first half, I'm going to be explaining a method for developing test scenarios. It can also be used for engineering and for design requirements and things like that. I'll be explaining the method in the first half, and in the second half, we're going to try it together and see how it works. We'll step through a case study. So let's start. Let's talk about a systems approach to safety-driven testing. The approach has a name. It's called STPA. Some of you may have heard of it. Some of you may not. It's System-Theoretic Process Analysis. But aside from the name, what is it? What is it for? This is a method to anticipate hazardous scenarios. We're trying to identify things like potential software errors, potential design errors in the system, flawed assumptions, which are really tricky. A lot of times they're not even documented as assumptions. The missing requirements or incorrect requirements, interactions between systems that nobody anticipated and leads to some unsafe or undesirable behavior, computer interactions, of course, and human behavior, which is really important, but very difficult to model. So you can apply to try to anticipate some of these dangerous things in the complex systems we're building today. There are 4 steps to the method. We're going to go through each of the 4 steps in a few minutes, and then we'll apply it to a real system. First, we're going to identify losses. So what are the things we want to prevent? You use this method to try to prevent some undesirable outcome. It could be loss of life, which is maybe traditional safety. Could be loss of mission or performance or anything that you want to apply it to just about. But we start with something we want to prevent at the highest level. Then we build a model called a control structure. I'll show you what that is and what it looks like. Then we analyze the model. We look for unsafe control actions. We'll talk more about what a control action is. If you're not familiar, it's based on control theory. Then we build these scenarios that can lead to the losses that we care about. So I want to start with the control structure. Once you understand the control structure, everything else kind of falls into place. So what is this model that we're going to build? It's not an executable model. This process could be started very early before you have a finished design. So on the left is a schematic, kind of a block diagram that most of you, I think, may be familiar with, some form of drawing like this, very, very detailed, kind of starting at the component level. And we want to get away from that. A lot of the accidents and the incidents that have been happening in complex systems in almost every industry, a large number have been traced to getting so caught up in the details that you miss the bigger picture. So we want a lightweight method that we can apply at a higher level of abstraction. So the insight behind a control structure in this whole method is, instead of starting at the component level on the left here, these very, very detailed interactions, recognize that maybe this group of stuff on the bottom, the application here is a satellite, but the application doesn't matter. The insight is, recognize that this group of stuff on the bottom, well, those are all the mechanisms we have to rotate or move the satellite around. Those are kind of the actuators. And the red box up on top of that group is essentially the decision makers. We'd call this a a controller, an abstract controller, even though there are multiple units inside. But together as a group, they're making decisions and they're providing control actions to try to affect and control those processes at the bottom. So we want to migrate from something on the left towards a higher level view on the right, where we have control actions to try to control some process, some feedback that may be used by a controller to monitor what's going on. Of course, how's that feedback used inside the controller? Well, every controller has something called a process model. What that means is basically a set of beliefs that the controller has about the outside world. Those beliefs can be updated and influenced by feedback and other things. And if those beliefs don't match reality, it's going to be very difficult for that controller to provide the correct control actions. A huge number of incidents are caused when this process model is out of sync. Not all of them, but a lot of them. We also have to look at a control algorithm, which at a high level basically says, okay, given these beliefs, what do we do about them? How do we decide the right control actions to try to achieve a goal? So this is very basic control theory, very abstract model on the right. It doesn't have to be executable on day one. And we can analyze this kind of thing on the right. We call this a control structure. Of course, this is only one control loop. In a real system, we'd expect to have more control loops. This is just the information I already described. We may have a hierarchy of control in a real system, right? We may have in a satellite, we may have an attitude controller, this group of things that is trying to decide where to point next. But then we may have some kind of navigation controllers deciding where maybe higher level decisions to try to command the attitude controller. So we have multiple control loops here and really a hierarchy, but we don't have to start at the low level on the left. We can start at a kind of a systems view on the right. In a control structure, we've got to manage complexity. It's one of the most important things in the analysis. So there are some rules to keep it simple and to keep it manageable. One of those is the the vertical axis means something. It indicates control. So boxes higher up have more control and authority over boxes towards the bottom. That means all of the downward arrows are going to be control actions. They're outputs. They're trying to exert some control to achieve an objective. The upward arrows are different. They're going to be feedback. They're kind of like information about what's going on that you can use, or maybe you may not use to make decisions about what to do next. So that's a very basic control structure on the right. We may abstract even higher and say, hey, you know what? All that stuff together, let's just bunch that all together and say, those are automated controllers. What's controlling the automated controllers? Well, we may have operators, human operators providing control actions and receiving feedback. Human operators also have a process model. Sometimes we call this a mental model that represents the human beliefs about the outside world. And if those mental models are not quite right or out of sync or not updated when they need to be, it's going to be very hard for them to issue the correct control actions to manage the process. Again, all of these rules apply at a higher level. This is the difference between a component view on the left and a systems view on the right. And this whole logic applies not just for software and for computers and automation, but for humans and human interactions. As I said, humans have a process model, sometimes called a mental model. Instead of a control algorithm, that's a very kind of computer or software-oriented term. But we might say procedures for an operator in an industry like aviation, where we have pilots that are given very careful procedures. Now, they may or may not follow them, but that's the intent. The same kind of logic applies for human interactions. In fact, we may want to go even at a higher level. This control structure on the left, where we had human interactions, kind of the operators, the boots on the ground, managing the automation. Well, we may have a lot of them in our industry or in our facility or maybe on our roads, and we may have some centralized control or some decentralized control. We may want to think about and engineer this first before we get into the details. So we can analyze at this higher level of abstraction, identify potential scenarios that can lead to misbehaviors and losses we care about, and apply requirements and constraints at this level before zooming in to the more detailed levels and way before we get to the component level. And we can derive test cases at this level of abstraction towards the right. So this forms the foundation for the process called STPA that I'm going to introduce. Of course, we can add detail later. That's never a problem with intelligent people. In fact, as an engineer, we tend to be trained to almost dive into the details right away from the start. Adding detail is not a problem. The difficulty people have in learning this is starting without the details, is resisting the temptation to dive into the component level view on the left here. But this is an iterative process. We do want to start at a high level and then add details as we refine later. Okay, so a little bit of theory that we're going to use to guide the process. When we look at control actions, there are 4 ways a control action can lead to a loss or lead to something we care about at a higher level of abstraction. If we have a control action that's needed for safety, but it's not given. By the way, when I say safety, I'm talking about any loss. It could be loss of life, but it could be a Mars polar lander that's going to another planet with no humans on board at all. NASA had a big safety program for the Mars polar lander. How, you might think, what does safety mean for an unmanned vehicle on another planet when there's not even a human anywhere near that can be hurt? Well, we can talk about safety in terms of mission loss. So really, anytime I say safety or hazardous or unsafe, I want you to know I'm talking about any loss that's important to the stakeholders. Could be loss of life, or it could be loss of mission or performance, or loss of customer satisfaction or anything else. So one way to have a loss is a control action was not given, it was missing. Think about a brake control action in a car. You don't brake when you should. Case 2, an unsafe command is given. Maybe you brake when it's a really bad idea, when there's traffic close behind and you're on a highway, for example, and you provide a large amount of braking. Case 3, maybe potentially the right control action is given, but it's a little too early or too late. So you provide the brake control action in a car, but it's 3 seconds too late. Maybe the right situation is just too late. So this is a timing related control actions that we care about. The last category has to do with duration. Maybe you provide the brake control action at the right time, it's on time, in the right situation, but we release it too early, so we only hold it down for 5 seconds, and it's not enough to slow down and avert the collision in a car or in an airplane or whatever. So these are the 4 categories of unsafe control that come from control theory. There are subcategories in each of these 4, but we can use this as a starting point to identify the things that we need to prevent in our system. And then we can build an analysis method based on those unsafe control actions. We can identify them. We can identify what in the world could cause them to happen, what kind of process model beliefs would lead to this, what kind of control algorithm flaws. We don't have to list every flaw that could possibly occur. That'll take forever, and it's not important. What's important is just the ones that can lead to these unsafe control actions, and we can narrow in on the things we care about. This is true when you're designing the system and coming up with requirements, and it's just as true when you're coming up with test cases or test scenarios. What are the cases that matter, the scenarios that matter the most? So we can use this to kind of direct our safety plan. And then we look at what if a control action was not unsafe, what else is left? The control action was just fine, but it wasn't followed or it wasn't executed adequately. Later on, you'll see this, but we're just not going to start here. It's too detailed to start here, but we are going to look at these different factors in building our scenarios. We'll want to look at things like a missing control action, ineffective control action, things like process models that are inconsistent or maybe just incomplete. Like initially the process model may be unknown when a computer is initially booted up, for example. We look at delays in the feedback, but also missing feedback because we never thought to include this feedback in the design. or maybe inadequate feedback because we had a sensor failure. So some of these scenarios do involve failures, but they involve a lot more than just failures in the safety world. We also want to look at maybe the control action we provided was the right one, but there was another controller provided a conflicting control action, and that's why it wasn't executed or followed properly. So we want to build these kinds of scenarios that would lead to an accident or to a loss of some kind, and use those to guide not only the design, but to guide the testing after the design. Or maybe during design, we should start building these test cases early, and maybe the engineers building the system can use some of these scenarios to do a better job up front instead of waiting for the finished product and then starting the testing process. Okay, so here's a high-level overview of the 4 steps in the method. So far, I've just talked about some concepts, but we haven't really gone through the steps. We're going to do that now. So first, define the purpose of the analysis. One of the most important parts of this is identify the losses we want to prevent. So let's do that. In a medical example, here's a patient-controlled analgesia. The idea is a patient may be in pain, and they can now push a button directly to have some pain medication injected into their body, so they don't have to wait for a nurse. Well, clearly this is a safety critical product. What are the losses? So a loss, super high level, loss of life, of course, or serious injury. But on the other hand, if the patient's pain is not relieved, that's kind of the mission statement. We care if we have L2, maybe not as much as L1, but we care if we're not relieving pain as well. We can use this process to carefully identify the causes of these losses. We can go broader and look at loss of protected patient information, getting a little bit into the security world. We can look at loss of reputation if you want. You can be as broad as you like. This is up to the stakeholders. In a nuclear example, we might look at human death or injury, of course, damage to the environment, but we might go broader. What about loss generation? Even if we don't kill anybody and we don't damage the environment, if we're not producing electricity and making money, we care. So we can identify scenarios that are going to lead to these losses, and especially scenarios that may present conflicts between these losses where we're going to cause one or the other, and we want to make sure we're doing the wrong thing. There's more to this step. I'll direct you at the end to the STPA handbook to learn more. But for the purpose of this short webinar, let's move on. The next step is to build a control structure. All right. Let me give you some examples. Here's an aviation example. This is a very kind of rough draft control structure, just to give you an idea. We may have some automated controllers in the plane, sending some control actions to the engines and to the ailerons and other control surfaces. We may have the flight crew kind of supervising that automation and changing the mode of the automated controllers. And who controls the flight crew? The pilots on the plane. Well, air traffic control. It sends some instructions and clearances to the flight crew. And all of these decisions, these control actions, are informed by feedback coming up. Here's a more detailed example for aviation. If you don't work in the aviation domain, this may not, some of these terms may not make a lot of sense on their own unless you're in the industry. But let's look at another example. Here's a ballistic missile defense system. We have an early warning system on the top. Sorry, this is a fictional ballistic missile defense system. It was a real project, but it had to be scrubbed to make it public. So we have an early warning system at the top that sends down a launch report to a fire control station, indicating that something was launched somewhere in the world and we've got to counteract it. The fire control station will send a fire enable command down to a launch station somewhere in the world. The launch station will then send a launch command to a computer on a missile, and the flight computer will send an arm and ignite command down to the interceptor hardware on the missile when the time is right. Every one of those control actions is informed by feedback that kind of bubbles up from the bottom to inform the decision and help the controller make the right decision. There's interesting flaws that you can look for, not just component failures, but interesting things like in different areas of the control structure, you could send an arm command and a disarm command. You may get a false alert and you want to go back to the safe state. Well, if this is sent through an Ethernet network, one of the big concerns was there's buffering and there are other things that happen through the network. We could send an arm command followed by a disarm command, but at the other end, what you receive could be a disarm command followed by an arm command, and that would leave you one step away from inadvertent launch. So STPA was used on this system to find a large number of scenarios just like that. That took a long time to address. Let's look at another case in automotive, adaptive cruise control. If you're not already familiar, they put a radar in the front bumper to detect cars in front, and this allows a computer to maintain a speed you program, but it will also watch for cars in front and automatically apply the brakes as needed to reduce speed. So let's build a control structure. I'll give you a little bit. Let's pull up the chat window. We'll start bringing some interaction here. We have a driver. All the manual commands are still there. Driver provides brake, accelerate, steer, and shift. And the idea is to add a computer in the middle, an adaptive cruise control module. What kind of commands do you think the adaptive cruise control module might send down to the braking system, propulsion system, or something else? Type your answer in the chat window. Got some good ideas so far. Apply the brake, release the brake, of course, yeah. I said it's also going to maintain some speed. How is it going to do that? What is it going to have to control other than brakes? Yeah, accelerate, maybe. Perfect. Thank you, Anders. Don't forget to change the to field down here to all panelists and attendees. There we go. Perfect. So here we have a control action. Let's start with accelerate and brake. Those are commands it's going to have to send. What kind of feedback might it need to receive in order to make those decisions? Distance to the car. Anything else? Speed. Perfect. So there's probably a lot in the real system, but we can start with some initial thoughts. Obviously, it's going to need speed. If it's going to maintain speed, it's going to need distance. If you think a little more, you might realize it needs some sense of whether the driver is trying to override so it can disconnect. So we can start with this. Now, this is not complete. There is more to it, but this is enough to start the analysis. If there are things missing in the control structure, that's okay. You just need a starting point. The rest of the steps will identify what's missing. Let's look above the cruise control module. What kind of commands would the driver maybe send? Increase speed, on or off, accelerate, yes. So basically what they're doing in the industry is copying all the commands from regular cruise control. That's the first two lines there, on, off, increase, decrease speed, and they're adding a new set of commands, increase and decrease the distance. What about feedback? Should the driver get any special feedback to help make these decisions? They should definitely get speed feedback from the system. That's probably, I might label it along this arrow. That'll give them distance. Is there anything they should get specifically from this cruise control module that they didn't have before? It may be weather would be important if there's some weather condition that makes the system not work so well. Is the thing on or off? That's a good, what's the mode? It may be some confirmation, particularly if this thing is capable of changing modes, if that gets proposed, but at least let the driver know if we're on or off and maybe what mode we're in. This is enough to start the analysis, and the rest of the analysis you'll see in just a moment. We're going to analyze these interactions, these controls. We're going to look for unsafe behavior and try to explain why this computer might do some unsafe things and why the driver might do some unsafe things, and build some scenarios. Here's a more detailed control structure. As I said, you can always add detail later and refine a control structure. That's not a problem, but it's really important to start with something simpler. Start with something like this so you don't get lost in the weeds, lost in the detail. Okay. I think maybe this one's a little hard to do in a webinar, I would have you draw our control structure, which is not good. We're not really set up for that. But you can read this description and tell me what kinds of boxes might be in the control structure. So I'll just read it out to you. This is shift by wire in automotive, if you're not familiar. This is changing the way the shifter works. We're talking about automatic transmission, park, reverse, neutral drive. Used to be a cable that goes from the lever down to the transmission, just clicks it into the right range. But we're replacing that now with an electronic lever, a computer, some electronic actuators, and the computer is going to be in the loop and send your commands on. So what kind of, but let's make a 3-box control structure. What might the boxes be labeled? Let's start with the boxes, then we'll do the arrows. Now it's kind of hard. How do you fit all of this into just 3 boxes? So we've got to abstract. Let's start with the thing that we're controlling. What are we trying to control? Yeah, so we are trying to, exactly, we are trying to shift gears. That means we're controlling the gearbox or the transmission. That those are things inside the physical vehicle. And what's controlling them? So we've used up one box. Let's just call it physical vehicle, and maybe the transmission is a part of it. What else? What's controlling them? An actuator, probably directly, right? In STPA, a controller has to have some notion of goal-oriented behavior. So it has to be making decisions. What kinds of things here would be making decisions and maybe commanding the actuator, telling the actuator what to do? Some notion of intelligence. Receiving feedback, monitoring feedback, using that to make a decision about what to shift to next. What does that sound like? Yeah, it's a feedback loop. So we've got a computer in here somewhere. That sounds like something a computer might be doing, might be monitoring feedback from some things happening, maybe some faults or something else. Yeah, and there's a CPU in the computer, and providing commands. What else, though? We have a computer. That would be a decision maker. We'd call that a controller for sure. It's sending commands to the actuator. Actuator is just kind of a pass-through. It's not, it could be more than that, but let's say it's just a pass-through. Just a motor receives the command and does it and obeys and shifts. What's controlling the computer? What's making decisions at a higher level to tell the computer what to do? Human, perfect, I love it. It's a little bit of a trick question because we don't usually, if we're doing a schematic, or electrical schematic or a software flow diagram or a lot of the other artifacts we do in engineering, we don't have a human, do we? It's not on the diagram because that's not what these diagrams are for. Well, this is a control structure. This is different. So if there is a control loop with a human, then we've got to include it. So that's what we're going to do. It's going to look like this, a little bit of a trick there. Because it's unusual, right? But very important for safety and very important in the analysis. Even if we're not, we don't engineer humans, we engineer the physical system and we engineer the computers. But even understanding how the driver and humans are going to interact are very critical for designing the computers and coming up with test cases for how the computer needs to react. So here's the 3 boxes we might have. The vertical axis indicates control and authority. So what kind of commands might come out of this computer coming down to the physical vehicle? What kind of control actions might we want to add? Yeah, there's a lot of ways to engineer this. So there's not a single correct answer. I do have a slide with an answer on it, but there's not a single correct answer. In an automatic transmission, you might design this at least to provide the commands or what range to go into. Park, reverse, neutral, drive, low. What kind of feedback might the shift controller receive to help make those decisions or know if the decisions are safe or not? Maybe something about speed that might be important for a park, current state, but current range, right? So the slides are incomplete as before, it's just a starting point. But we might start with something like this and analyze it with the remaining steps to see what's missing, or if something is really critical that's missing. What about the driver? What kind of commands might the driver provide to this computer? This is a simple control structure, nothing fancy here. Yeah, it might have the same thing from the driver. Change gear, park, reverse, neutral drive, and then we have a shift controller. And you can see what's going on here. If we're putting a computer in the loop, you kind of think, well, why bother? Well, kind of because they can, I guess. It's happening. But there are some things that the computer, some proposals that the computer may want to override the driver in certain cases. Some dangerous things potentially could happen there. So clearly we want to be very careful about designing this and about testing this. Make sure we don't do the wrong thing. What kind of feedback? We're missing feedback to the driver. Should we add something here? Yeah, maybe at least what's the current range? What's the current gear that you're in? Especially if somebody's going to be proposing overriding these driver commands. If the driver says go to park and the computer thinks, well, maybe that's a bad idea, I'm going to override you. Well, now we've got a really critical feedback for this brand new situation that didn't exist before, where it's going to actively throw out these commands because it thinks it knows better. So that's really important, even more important than it is today, to let the driver know, did we follow your command? And that can raise some really important human interaction issues. But it's not a human issue. It will impact how we design and how we test the shift controller. We've got to find ways to bring humans or human considerations into test scenarios that we're doing today. This is one way to do that. So it works really well for human interactions, but it also works well for software interactions. All right, let's move on to the next step, identify unsafe control actions. To do this, we're going to look at a downward arrow. That's a control action in the control structure. We're going to identify these 4 ways that control action. All right, when you identify these 4 ways, you look at how can providing cause a hazard or a loss, how can not providing cause a problem. We translate these all into functional safety requirements or controller requirements, and they look like this. Controller X shall provide this command when D. Does that look familiar? Controller X shall not provide this command when E. You might not like the shall nots. I completely understand. But there are things we don't want to happen. You can call these requirements or something else if you want. The method, or you can ignore them if you want, but the method will produce them. They're both important. Control X shall provide this command when within Y seconds of F. These are very specifically and precisely defined. They always have these same ingredients, and they're written to be test-oriented requirements, and these can be used to drive our test scenarios. But we're not done. These are just the control actions that we want to prevent. These are the ingredients to an unsafe control action. We always have a source control, where it came from, the type, is it provided, not provided, or what, the control action itself, and then the context that makes it unsafe. This is a reverse thrust command is for an aircraft. It's similar to a braking command. It's one of the mechanisms to help stop the aircraft. So if I told you the computer does not provide this command, let's say at 8:30 a.m. this morning, was that unsafe? You'd say, well, I have no idea. What's the context? What's the environment where that happened? The context always matters for safety. So if I told you the aircraft landed and the computer did not provide this reverse thrust command, then you'd say, wow, well, that's very dangerous. That's something we never, ever want to happen. So this is the structure of an unsafe control action. We can refine these a little more. We don't need to during this presentation, but there's a lot more out there. This is basically talking about the context that could trigger an unsafe control action. We want to test for this. We want to try to recreate this in our test scenarios and verify that it's not going to provide the reverse thrust command. Or we could verify in another type, verify that it does provide some other action in that context. So we can translate these as needed. So here's the translation. The computer does not provide reverse thrust command when aircraft lands. That's very dangerous. So what are we going to require? What are we going to test for? Let's make sure that the computer will provide the reverse thrust command when the aircraft lands and reverse thrust is armed, for example. Okay, let's go on to the last step, these scenarios. So far, we just looked at the control actions coming out, but there's a lot more going on than just control actions. What we want to do is this white arrow is showing an unsafe control action in some controller. This is the output of the controller. So we just identified lots of ways that the output could be dangerous and things we want to prevent, but let's expand our scope and look at the rest of the system. Let's build scenarios for the controller behavior. I'm talking about maybe a transfer function that's unsafe that we want to prevent based. We can derive that from the unsafe control action. Just translate the context into a type of feedback. Then you get your transfer function, inputs to outputs for the controller. We can do something very similar for the feedback in our system. To build these scenarios, we can do this for the control path. Say the output was correct, but it didn't work. It's as if we had an unsafe control action because it didn't work. Something went wrong through the control path. We can derive these scenarios, case 4, for inadequate process behavior. So here's a way to think about that. Starting with the unsafe control actions, let's build a scenario that explains how they could occur. Let's say, what does the controller maybe believe that would lead to this action? What kind of control algorithm characteristic would lead to this? What kind of feedback, missing or incorrect, would lead to this? And we'll build a scenario at a high level, not a 100-page report or something, but really something that would fit on one slide. Build a scenario that shows exactly how this might happen. Now we'll tell the engineers how to build it better, and it will tell us how to test it better to try to see if we can get that to happen. We also look at the inverse case. What if the command was the right thing to do? It was safe, but it was not followed or executed. So we come up with these scenarios that say it was this critical command, not all commands, not all contexts, but this critical command in the critical context was not received for some reason, or was received, but it was ignored by design. It's a really tricky one to deal with when we have multiple controllers in our system. So we'll drive not every possible conflict again, but just the ones that matter that will lead to the loss. So we can use this to help guide our scenario development to try to make sure we have coverage over each of these factors. We'll look at process model flaws inside the controller. We can do this black box view of the controller, but even before the thing is designed, we can build these because we know from control theory, every controller has a process model. If it's going to be a controller, it has to have a process model, so a set of beliefs on the outside world. And we can identify at a high level, at an abstract level, what those beliefs will be even before the thing is designed. And at the end, we come up with design recommendations, component requirements, test cases, and other things. Exactly the same process applies to a human. These are the same slides, so I'm just going to go a little quicker, but it's exactly the same thing to look for human interaction scenarios that we're going to have to mitigate or be able to handle in a safe way. So we look for unsafe control actions. Look at those 4 categories of unsafe control from a human. Then we look at what we build, maybe not human requirements because we're not engineering or human, but operator procedures. And then we can build test cases that try to see or verify if they're going to follow these procedures, or maybe build a test case or a scenario that would make them want to violate these procedures. And these are not every procedure you can define. These are the ones specifically that need to be enforced to prevent losses that we started with. Then we build scenarios. We say, okay, what in the world would cause a flight crew, maybe a well-trained, very intelligent flight crew to deviate, or to maybe not deviate, to follow a bad procedure and issue this unsafe control action? What would they have to believe at the time? And what kind of feedback could our system provide that would cause them to believe those unsafe things, or maybe cause their mental model to go out of sync? We'll build those those scenarios, and it's not hard to see how we can build test scenarios from that. It's exactly the same process. How can we kind of muck things up by taking a correct or safe control action from the flight crew and then making it ineffective or not followed properly along the way. And we'll build these scenarios, build design decisions, requirements, and test cases. All right, so there's the full process. We went a little quickly at the end there, but we're going to do it once more, and we're going to do it with a real test case. We're going to do it interactive. So let's do a self-driving car. Let's walk through each step of the analysis. First step is to identify some losses. I'll give you one. Loss of life or serious injury will be one loss we want to prevent. We can use the process to figure out scenarios that would lead to that loss. What other losses might you think about? Let's say nobody dies and nobody is injured physically. Is that it? Is there something else we care about preventing? Cost, of course, yeah. Loss of property or damage to property. You guys got it, perfect. Damage to vehicle. We always want to think about mission. Mission is transportation in this case. So if we don't crash, we don't damage the vehicle, we don't kill anybody, but we never get to point B, we care, right? Or if we do get from point A to point B, but we lose customer satisfaction along the way, maybe it's inefficient or something, we care. So we can look at all of these losses and some others if you have other losses in mind. All right, let's move on to the next step. Let's look at a control structure. In the interest of time, I'll give you a very high level control structure and you're going to help me analyze it. Super high level control structure. This picture in the top is a Google self-driving car, but lots of companies have similar high level control structure. We have it's common to have a safety driver, a human in the case for public road testing of these things, and they basically have a big red button that they can mash to stop the car if they see it doing something unsafe. And we have this autonomous software. Let's abstract lots of details in here, put this lots of things into one box and say at a really high level, it's going to make some fundamental decisions. It's going to decide to change lanes. It's going to decide to go and decide to stop and maybe a few other things. Let's start here. And you'll be amazed at what you can get out of a high-level control structure like this. As I said before, you can add detail. That's not a problem. We're just not going to be able to do that in 15 minutes in a webinar. That's all. But I'll direct you to other papers and publications where we can look at much more detail than what we'll do now. But let's run with this. Let's see what we can get out of a super high-level control structure. Does this make somebody stop me if you want me to explain this a little more, but I think this is kind of clear. Even if you're not an engineer working on self-driving cars, I think this is fairly straightforward to understand. We've got emergency stop control action up here. And we've got some very basic, very abstract control actions from the software. So let's move on. Let's go to step 3, identify unsafe control actions. Let's look at the downward arrows here, okay? So we've got lane change, go, stop. Let's look at the lane change command. Now you're gonna help me. Let's look at this column right here. How could provide the lane change command cause a collision? Let's start with that kind of loss. Is there any way lane change command could lead to a collision? How? Right, if there's a vehicle next to a car, let's be a little broader, when there's an object near, if the lane is not clear, perfect. Now, notice when you're coming up with unsafe control action, there are 4 ingredients. We always want to think about the source controller. So if we're being super formal here and trying to be very precise, we would say autonomous software, that's the first word, provides, that's the column we're looking at, the lane change command, and then we would say when, and all the things you're giving me are the context here. So excellent, you guys are picking this up very quickly, exactly. So we'd fill in, basically these 3 are given to us by the control structure and by the table, and our job is to fill in the context of the UCA. So here's one, when some vehicle is in the path. Clearly, that's dangerous. We don't want to be changing lanes when there's a vehicle in the path. There are others, as you guys have been mentioning. Let's take this one and chase it further. All right, so here's what we've got on the control structure. We've got an unsafe control action here. We don't know if it's really going to be provided, but we know that it's dangerous and we've got to prevent it. So we've already got the beginnings of a test scenario. If we ever, in any point of our testing, see this unsafe control action, we've got to flag it and something's gone wrong. But let's get more detail. Let's build something. Let's see if we can identify, even keeping software as a black box, how in the world some piece of software would do this, all right? Just by understanding that every software, no matter how you design it, it's going to have a process model, it's going to have a set of beliefs. So let's start there. Let's build a scenario. We're going to use this to kind of structure our thinking. I like to start with the process model. Here's an unsafe control action. Remember that the output, and we're going to work our way backward and see if we can build a real solid scenario that explain why this would happen. My animations are messed up. So let's look at beliefs. What in the world, we'll take this unsafe control action, but what in the world would the software have to believe to provide this unsafe control action? Give me some beliefs. Belief may not be correct, may not match reality, but it's a belief. Yeah, right off the top, if it believes there's no car there, clearly it's going to do that. Now, there's probably at least one more. What if it believes there is a car, but what? Is there a case 2? But it's far enough away, but there's room to move, or it is moving, right? So there's something else there. Exactly, you got it. So we might write it like this. So we believe there's no obstacle, that's case 1. Or if we believe there's a vehicle or an obstacle, but it's far enough. Look at this. This is almost exactly what you're thinking. Perfect. And there are probably other cases. But let's start with these two. Let's look at number 2 in a little more detail. Let's chase that one a little further. All right. Now, let's look at the control algorithm. Now, I'm not giving you any lines of code. I'm not giving you a piece of software to study, but just by the fact that we know there's going to be some software making these decisions, what can you say at a high level in terms of how a piece of software would determine that it's far enough away? What does that mean? I mean, software is basically math, right? What kind of factors would it have to look at to figure out if it's far enough away? Speed and distance, that's right. Yep, so speed is velocity, yep, and distance. Is there anything else? Is that enough? Speed, yep, so speed of the other vehicle. So speed would have to be relative speed, right? That's what matters. And distance would probably be relative distance. Think back to Physics 101, the kinematic equations. If you can think back that far. Yeah, so the direction of the velocity matters. Well, if you went back, if I gave you more time to go back to your Physics 101 equations, do you remember 1/2 AT squared plus V naught T plus X naught? Yeah, there are a bunch of those. They're called kinematic equations, and you typically go look them up. You don't rederive them from scratch. So it's a little not fair that I'm not giving you time to do that. But if I gave you some time, you'd go do a search and you'd find out, here's one, and this one fits our problem. You need to figure out if the distance is at least as far as this. We'd look at relative velocity over 2a. Now, the distance is clear, that's relative distance. V is clear, it's relative velocity. A is not so clear because it's not instantaneous acceleration. Now, think about it. The way to see this in plain English is let's say you're in a car, you're pulled over on the side of the road, you're stopped, your velocity is 0. A car is coming in the lane behind you, and it's going, let's say, 15 miles per hour. And let's say it's 20 feet away. Do you cut over? Is there enough time? Technically, it's a collision path, but how do you define the threshold? Well, what it comes back to is different ways to specify in terms of T or a distance, safety margin, or whatever. But one way to define it is an assumption about the acceleration of the other car, not the current acceleration. Let's say the current acceleration is 0. It's a constant velocity. It may be okay to cut in front. It's your assumption about what they're going to do when you cut over. You assume that they're going to decelerate by some amount, and you're going to be okay. So relative, to be technical, it's relative acceleration because you're going to be accelerating as well. It takes a little bit of thought to get there. Here's a way to see it. Let's say we keep all these numbers fixed. You're stopped. An obstacle or vehicle is coming at you 15 miles per hour and it's, let's say, 30 or 40 feet away. Keep all those numbers fixed, but it's a small, tiny Toyota Prius. Maybe you feel like, yeah, that's fine. I'm going to cut in front. There's going to have plenty of time for that thing to slow down. Now let's keep all the same, and instead of a Toyota Prius, it's a freight train. Do you cut over? Probably not, right? Because you know freight trains don't stop on a dime, and you're going to have a different, the D is the same, the V is the same, it's A that's different. It's your assumption about the deceleration capability of that vehicle. That's what it comes down to. And you can rewrite it in a lot of different ways. But let's use this, and here's the kinematics equation there that you would use to drive this. So let's start there, and now tell me something about, so that might be a control algorithm. So if D is at least that big, you get that. Now, how would you compute this equation? Where does D come from? Is there some input that provides a sensor? Yeah, maybe a LiDAR sensor, right? They report relative distance to obstacles. I mean, there's processing that needs to be done, of course, but you would get a distance out of that processing, right? Out of a LiDAR, maybe. The picture there has LiDAR on the roof of the car. So that's how we would get D. Now, let's say what kind of feedback would cause this equation to evaluate incorrectly and cause process model belief number 2. What can we say about D being reported? Would D too high or too low cause this? Yeah, so somehow the measured distance is higher than the actual distance. So the actual distance is too low, is what would cause this. So if we measure somehow, whatever feedback we use, if the measured D is too high, that would cause this to evaluate incorrect. It would cause this incorrect belief number 2, and it would cause this unsafe control action number 1. Let's do it for a V, relative velocity. What kind of measurement, or how can we characterize a problem in feedback for V that would lead to process model flaw number 2 and UCA number 1? If the measured speed is what? Yeah, right, remember this is relative velocity. So if the measured relative velocity is lower than it really is, so if you think, if the true state is they're coming at you really fast, but the measured indication says it's not that bad, the relative velocity is pretty well matched, you may feel like it's okay. You may feel like it exists, but it's far enough away, and you may merge into the lane, UCA1, right? You see that? What about, now it's not just any error in velocity, there's a particular direction that matters that causes this scenario. Same thing for D, there's a particular direction that matters, not any error. All right, and what about A? What problem in A would cause this? Remember, A is deceleration capability of the other vehicle. Right, so if you think, for whatever reason, that the other vehicle can decelerate, negative acceleration, right? If you think it can decelerate much better than it really can, you're going to think it exists, but it's far enough away, and you're going to lead to UCA1, right? So where do these come from? D comes from LiDAR, probably. Where does V come from? Where would you guess? From another sensor? V can come from radar, right? We get range rate and other things. Well, now what about A? A is deceleration capability. It's not instantaneous. So where would you get A from? Well, it's really tricky to get A because it's not instantaneous. It's future deceleration, right? So you can do something like characterize the vehicle and try to do some image recognition to figure out how big the vehicle is. That doesn't work so well, or not super reliable. So what you can do, and what some manufacturers have done, is assume a fixed value for A. Anyway, here are, before I get too far, here are the scenarios that we came up with so far. If somehow the measured distance is too high, that would cause this to evaluate incorrectly. It would cause belief number 2 and would cause this unsafe control action. You'll merge into the car and you think you have enough time. If the measured velocity is too low, that'll cause this. And if the deceleration capability that you assume or measure is too high, that'll cause this. So let's change this up a little bit. We're just about done, but I'm going to play the role of an engineer who's building this system, and you're going to play the role of a tester developing test scenarios, and you're going to ask me, you've identified this as a concern or as something that would lead to this unsafe control action, and you're going to ask me some questions about these bullet points to try to figure out if they could happen and how they could happen. What kind of questions come to mind in terms of building a test case? All right, let me answer the sensor error. I will tell you that for the first 2 bullet points, we get very accurate feedback directly from the sensors. And we have these calibrated very carefully. I know that your good testers will question everything that I'm saying. We have carefully analyzed and already thought of these cases where the sensor can fail and the sensor can report something dangerous. So at least for the first 2 bullet points, those come directly from a sensor within tolerance. We compare lots of different sensor data and make sure that they're within tolerance and they all agree. Otherwise, we go into a safe state. But that's for the first 2 bullet points anyway. There could be a person crossing the road. We have LiDAR sensors that are really good and have already been tested carefully for people crossing the road. Try to stay grounded in these bullet points on the right-hand side. Use this, I want you to think outside the box a little bit, but ground yourself in these. How the calibration is maintained, that's done by the manufacturer through careful processes. They're following other people already. There's not really a concern about calibrations of these sensors. But there is a concern about the last bullet point. We don't have any calibration for the last bullet point because it doesn't come from a sensor. The way we handle weather conditions is if we ever have any adverse weather condition, we stop testing. The human will stop testing, or we won't start in the first place if there's any forecast. So I'm obviously leading you towards certain scenarios that I want to try to capture in the time left. We looked carefully at the first 2 bullet points on the bottom right: measure distance too high, measure distance too low. We identified cases where we want to make sure it's calibrated properly. We want to but we have not explored that last bullet point. That's where we are right now. I haven't even told you where it comes from. It does not come from the braking system. Remember, A is actually the deceleration capability of the other car. It's an understood what we believe the other car is going to do after we move into the lane. How quickly we think that they're going to decelerate. How is detection capability measured? Thank you, Anders. Well, turns out we know turns out we know already that although we could use image recognition through a camera to try to detect how big the vehicle is, we also know that that's very unreliable. So we don't do that. We use a fixed constant for deceleration capability, and we just plug it into the software. Do you have a follow-up question about that measure? Or how we came up with it? Thank you, Fiona. Well, we very carefully didn't just write something down out of the blue. We did a careful study. We measured deceleration rates of vehicles on this test route over a course of weeks and months, and we took an average value for average deceleration of all vehicles, and that's what we're using in the software. And by the way, we're using it right now, so I don't really feel very concerned about this. How do you feel, and how does this influence your test cases or your test scenarios? Don't trust. Well, obviously don't trust. You're correct. Someone give me a test scenario. I'm going to play the role of the developer, and I feel really strongly that this is the correct design decision. We don't want to be over conservative, so that's why we chose the average. And by the way, the average value is not just used for this equation. It is used for this equation, but it's used for lots of other things. An average was the mean. It was the best optimization of all the goals that we have. We don't want it sitting there either. Yeah, so we assume it's an average vehicle with an average deceleration capability on the road derived from real data. And that's what we use in this algorithm to determine if there's enough time for us to merge over into another lane. Now let's say, yes, so let's say that we're having a disagreement right now about whether this is a real problem or not. You're on the right track, by the way, but I'm playing the role of a developer and I'm not so concerned. Give me a test case that's going to convince me. We're doing public testing on the road. We can also do testing on a test track. Give me a test case that you think will demonstrate vulnerability or weakness if there is one. What do you think we should do on the test track? Verify when a Mack truck? Sure. Merge. You've got it. I'm trying not to put words in your mouth. I think you've gotten it. Give me a scenario. You put a car on the road and what? You have a Mack truck following and you do a merge into a lane with a Mack truck behind. And see what happens. Maybe you want to do this, maybe not on public roads immediately. Maybe you want to do this on a test track with a control scenario or something, but so we don't actually crash. Put something behind the vehicle. Now, should that something be something lightweight, something heavy, small car, big car? Doesn't matter. Something heavy. Right, you got it. So that's what's going to violate the assumption that we made when we designed the software. I don't know how contrived this example appears to you, but this is real. This is a real case. It's very similar to what companies have done on public roads today already. We have had crashes reported due to essentially this kind of problem in California. Due to this exact type of assumption and this average behavior that was assumed and was not discovered. And what was done is, the strategy is to do 1 million miles of testing, which is not enough, but a huge amount of testing to try to uncover these by chance. And we've had cars that have driven huge numbers of miles with this design and did not cause a collision until one day, a couple of years later, finally we did have some collisions. that were reported based on this kind of flaw. So this is very real case. If it seems obvious, that's, first of all, it was not obvious at the time, but I agree, it does appear obvious on this slide because of the way it's presented, because we did not start at the component level. We did not get carried away in the details. We focused on this entire software as a black box, on general process model beliefs that will lead to these general unsafe control actions. And without giving you a line of software code, without even giving you the assumption, you were able to come up with these bullet points on the right, these general cases that would trigger this unsafe control action. And then at the end, I wanted to see how close you could get to identifying the flawed assumption if we had some interaction with the developers, and you did. So that's great. Anyway, this is a very quick webinar version of trying to do it in a few minutes. Obviously, you wouldn't want to do a real study in just a few minutes. You'd want to spend a lot more time on it. But I wanted to give you a taste for how this kind of process works at a super high level. There are more resources available to you to apply this at a more detailed level and to get much more carefully. Every part of this has traceability, which I regret I don't have much room to show on this slide. Every scenario is traceable to an unsafe control action, which is traceable to a loss, so you know where they all came from. It's been used in autonomous vehicles, in aircraft, avionics, in the chemical industry, nuclear industry, all over the place to identify these types of cases before they happen. Try to identify flawed assumptions, missing feedback no one thought should be important, missing or incorrect requirements, and interactions that nobody thought of. So anyway, it's a quick high-level view. I hope this inspires you to go Google the STPA handbook if you want to learn more. Particularly chapter 2 is the how-to guide. And of course, you can always email me if you have any questions. My email is there at the bottom. I'll be here for a few more minutes if anybody has questions and we want to have more of a Q&A. I'll be here for a few minutes, but this is the official end of the webinar. Thank you, everybody.
Thank you, John. I may add that I've used it to test systems, processing huge amounts of money, and discover some design flaws too. So yeah, it's really useful. Perfect. Even in IT.
If anybody does have questions, please feel free to put them in the chat window. Is that where we want to direct people?
Yep.
Perfect. Oh, perfect. Thank you, everyone. I'm glad you liked it. Well, sorry, I see a question. There are, I'm not sure, Anna, if you had in mind automotive industry. It is being used quite a lot in the automotive industry. I don't know everyone who's using it. There's no requirement for people to tell us. Everything's out in the open. You can read about it and use it immediately. You don't have to pay royalties or worry about IP or any of that stuff. Our mission is just to make these available to the world. So we don't know everyone who's using it, but the people we do know, we looked at the US market share of the companies, automotive companies using it, and it was just above 70% of the US market share. So a huge amount of companies, OEMs mostly, but starting to be suppliers using this process, not just for testing, but including testing. Now, it's being used for autonomous cars as well as ADAS. If we had time, I have another ADAS example that I was going to show you. If you're not familiar, by the way, ADAS is not fully autonomous. It's just driver assistance features. Anytime that you have software or automation of any kind, whether it's limited automation or full automation, this process works really well. The other place this works really well is if you have human interaction, with or without software. Any kind of human interaction and potential for human confusion, human mistakes, we would say mental model flaws or inconsistent mental model beliefs. This process works really well to anticipate those and to, before an accident, and to drive our testing and our training. Yeah, the folks at GM who developed Super Cruise are big fans of STPA, of course, particularly Human Factors Group, but also some other folks there. They've said this publicly. If you look at our website, send me an email. If you can't find our website, I'll direct you to it. They have a presentation where they gave, I think they gave one before and one after Super Cruise, where they were talking about the GM system safety process, which includes STPA. But it's not just GM, it's lots of companies, and it's not just automotive either. Could you use the method for sudden unintended acceleration? Yes, absolutely. So I focused on a method called STPA, which is meant for anticipating accidents before they happen. There is a version of this. Everything is the same. You have control structures, unsafe control actions, and so on. But the method is tailored to investigating accidents after they've happened. And the word for that is CAST, C-A-S-T is the name of that method, causal analysis using systems theory. It's the same idea, same concepts, but it's a little easier actually after an accident. A lot of the answers are right in front of you. You don't have to come up with scenarios from scratch. Yeah, good insight there, Anna. And beliefs is really important, not just for humans, which we need to do a better job in testing, anticipating how humans are going to interact. But it's also a great way to abstract software behavior without having to read through hundreds of thousands of lines of code in the software, but still do something intelligent in the software.
Interviews are very good at mapping out how people manage a complicated system. Some of the systems I've been testing, we have several source systems feeding data into the system, and we have money handling systems, and we deliver them out to the systems, and they're all in different organizations. And STPA helps me, and the control structure helps me to kind of get a high level grip of what are the dynamics in the whole system, and who needs to be coordinating and who's getting informed. So that's kind of the context I'm using it in, which is very different from a car, but not that different when you start to think of it. You've got a lot of computers interacting with each other and a lot of humans around it. Interesting, Fiona.
I'm just scrolling through to see if there are any other questions I may have missed. Right. One of my personal criteria for applying this method in terms of success criteria is it's got to uncover something we didn't think of beforehand. Otherwise, it's just a paper pushing exercise. We've got plenty of methods that are kind of paper pushing or documenting things we already know of. This is really intended to be a method of discovery, of realizing some interaction or some consequence that nobody may have thought of beforehand.
I could argue that sometimes you're in a context in which you need to document what you have, and then the fact that you have this full traceability in STPA of what kind of model did you think about and how did you come to this realization of a problem? Are you sure this is a problem? Right. You might see it before you do the STPA and then redo it there, but then have it documented in a better way. That's just one observation I've done. But I agree, it is for discovery.
Okay. Well, I think we have addressed all the questions. I'm not sure if my double check me if I'm missing any questions. My chat window keeps changing, but I'm not seeing any new posts. So there might be a bug somewhere or something I'm not noticing. Perfect. Okay. If there are no other questions, I think I will end. Here's a question. What future trends do you see emerge in the future? Well, there's a trend emerging right now. I'm coming at this from the safety world. I used to do testing and verification of things like FPGAs and ASICs before I ever learned about safety. But from the safety point of view, we're seeing a trend, a very important trend in the types of incidents that are slipping through the cracks of unintended and unsafe behaviors in our systems that are slipping through every control we have, including testing, but everything else as well. And that is the interaction problem. We have traditionally focused very carefully on what can go wrong when components break, when components fail, individual components or combinations of components, and there are probabilistic and other techniques to try to carefully examine that problem. But there's something that's missed. What if every component works exactly as designed? Now that's really tricky. That's if every component works as designed and somehow leads to undesired behavior or an accident, that's obviously really important. But think about all the controls we have in place. We have in testing, there's a big emphasis on requirements-based testing, right? Or requirements-driven testing. How do you define your test cases or your test scenarios? Well, look at your requirements to start with. If it's required, then we want to make sure we have a test case to show that it really is satisfied. Well, if the problem is with the requirements, we're not going to find it with that kind of testing. And it's very tricky to develop those kind of test scenarios to capture what's missing in the requirements that no one thought of. And these are what's called sometimes interaction accidents, not component failure accidents, or not just a deviation from requirements, but what if the requirements themselves are the problem? Now, we have unit testing and component testing, and we also have system testing, and that's the real difference between unit test or component test and the system level or vehicle level test is, I mean, if all of our requirements were right, you might think that component testing would be enough at the end of the day. Just test all the components, and of course you plug them all into each other and do that integration, you'll never have a problem. Well, that's not reality. We always have trouble during integration in testing. Most of the biggest problems we find are at the system level, not at the component level, and a lot of this comes back to missing requirements that no one realized would have this unintended effect. But every component at the component level behaves as designed or as required. So that's that's a big trend. It didn't used to be that way 30, 40, 50 years ago, but it is definitely that way in the last 10 years. If you look at accidents, things where people have actually died, almost all of them are traced to this interaction, this requirements problem, this integration problem, not the component problem or the component failure problem. So it's really tricky to capture. And that's one of the things this method is designed for. But just in terms of general trends, that's a big one. If you're in the automotive industry, this will sound very familiar with you. They just came out with a standard called SOTIF, Safety of the Intended Functionality. That's the whole basis for the standard. They recognized that the existing processes were so focused on malfunctions and component failures that what was missing is, what if the intended function was satisfied correctly, but it was not safe? It was not what was needed. The intended function itself was dangerous. So that's the safety of the intended function standard coming out in automotive. It's called SOTIF, S-O-T-I-F. Exactly, yep. the IT systems are a very familiar problem where components work as designed, but the system may fail. It's absolutely because systems are more complex. That's what's happened. 30, 40 years ago, we could conceive of basically through unstructured methods like design reviews, we could, not completely, but more or less, we could uncover the design flaws and the requirements flaws that mattered. But now, today, the systems are so complex, there's no one person that understands all of the interactions, and it's no longer effective to use these unstructured methods to try to think about all these interactions. We need careful processes to systematically examine what can go wrong, not just what can fail or what can break, but what can what can go wrong even if the components work as designed. It's also changing because in automotive and other industries, historically, we've carefully engineered these systems so that they have different disciplines, right? We have chassis, we have steering, suspension, braking, and those systems don't interact with each other historically, or 30, 40 years ago, right? They're very mechanical designs with limited interfaces, limited interactions between them, and you could roughly design them in different teams that don't really need to communicate with each other so much. Well, that's all changed in the last 10 years. Everything is computer controlled, and those computers talk to almost every other computer on the car. And those are the interactions that are getting lost because we have teams that design each component or each subsystem, but the interactions and dependencies and the communication between those teams are not quite what we need them to be, and things are falling through the cracks. This is another form of complexity, interactive complexity, right? I love this question about the 737 MAX. I will take a more detailed answer offline. I would be happy to. But online, we had a different webinar where we applied it to that scenario and had some very good results. This method, I mean, that's the scenario, it's more complex than what you'd realize in the media. But I've been studying very, very carefully and trying to limit what we say in public at this stage for a few reasons. But this kind of accident is everything that we've been talking about. It involves interactions at the system level, where examining things at the component level can make it the problem much more obscured, and some of the assumptions that were made make a lot more sense on the component level, but at the system level, that's where the problem is, at the system level. You also have you think about a failure-based mindset and assumptions about crew response and even about computer capability, and those assumptions can change over time. The only way to anticipate that kind of accident or anticipate the scenario, the assumptions that were wrong, is something like this technique. This is not the only technique, but something like this, to carefully look at those interactions. So you've got to look at human behavior, software interactions, and hardware all together. If you look at any one, you can easily convince yourself that it's fine. But you've got to look at all three of those together to see that kind of problem. There are limitations to STPA. One limitation is I'm a big fan of STPA, so I would say it's both a strength and a limitation, but it does not. So the limitation would be it doesn't produce a reliability number. The advantage would be it doesn't require knowing the reliability of the components either. So if you need to develop something like a maintenance schedule that says how many hours of operation can go by before you need to replace these components in a safety critical system, well, STPA is not going to provide that answer. And it does impact safety, it's important, but it's not going to give you a number of hours for a maintenance schedule or requirements like that. You won't, those are really reliability requirements. You won't get those. That's not what STPA was meant for. STPA is meant for functional interactions, functional problems in your system that you might not have anticipated. And for that problem, it's very good. Yeah, Internet of Things. A lot of people have given, a lot of people working with Internet of Things are also starting to apply STPA to that problem. It's starting to get a lot of attention there. In testing, I know some people on this call are very interested, but there are a lot more engineers using STPA today than testers. So I think it's a real opportunity for testers. Relatively newer in testing, I think, but very applicable to your job. Okay, I think maybe that's it.